So this is lecture 7, Sum and Difference Identities, day 2. We're going to walk through 3 proof examples and then 3 examples that will show up on the application section of the unit test, all about figuring out the sum or difference of 2 angles, but looking a little bit different with trig inverse things. So let's start with the proofs first. This is example A here. We have the sine of 3 pi over 2 plus theta. We're trying to prove that it's equal to negative cosine theta. On this one, I would start with the left-hand side because it gives us a few more options here. But essentially what's happening is we have the sum of 2 angles. Angle A being 3 pi over 2 and angle B being theta. We don't know what theta is. We'll leave our final answer in terms of theta. But we have an expansion for the sine of A plus B. Remember, sine of A plus B, that's sine, cosine, cosine, sine, sine, cosine, cosine, sine. So this is going to be the sine of 3 pi over 2 times the cosine of theta. And then with sine, the expansion, the sine stays the same. So if it's A plus B, then it's plus here. And then the cosine of 3 pi over 2 times the sine of theta. And then we can use the unit circle to evaluate the sine of 3 pi over 2 and the cosine of 3 pi over 2. The sine of 3 pi over 2, remember 3 pi over 2 is 270 degrees, it's negative 1. And then the cosine of that is 0. And so what happens to that second term is it all just goes away. And we're left with negative cosine theta, which is what we were looking for. Now we used the sum difference or the composite identity here. And then we use the unit circle for that second step, so I actually don't need to mark anything or name anything because we didn't use a trig identity on that one. Alright, so example B, there's actually a few ways you can go about doing this. If you started on the right-hand side, you'll get there, and it's very straightforward actually if you turn cosecant and cotangent into sine and cosine and then figure it out from there. Just for the sake of practicing a different option, I'm actually going to start on the left-hand side, and the first thing I'm going to do, we don't have an expansion for the secant of A plus B, but I can turn secant into cosine. Secant is 1 over cosine. And so this becomes 1 over the cosine of alpha plus beta, and that uses the reciprocal property. And then after that, we have an expansion for the cosine of A plus B. Cosine A plus B, that's cosine, cosine, sine, sine, cosine, cosine, sine, sine. So that's going to be the cosine of alpha, cosine beta, and then with cosine we change the sign, sine alpha, sine beta, and that comes from the composite or the sum difference identity. And then there's a few steps you can do here. Now, we're trying to get cosecant alpha, cosecant beta in the numerator. That's what we're trying to prove. At some point that cosecant alpha, cosecant beta is going to get to our numerator. So that kind of gives us a good place to start the next step. In order to get cosecant alpha, cosecant beta to the top, to our numerator, I can multiply this whole fraction here by the cosecant of alpha, cosecant beta, over cosecant alpha, cosecant beta. So that essentially becomes my fancy form of 1. And there's no identity to list there, we're just doing math. But when I do the multiplication here, we end up with cosecant alpha, cosecant beta on the top. And then cosine alpha, cosine beta times cosecant alpha, cosecant beta. I'm going to leave that because that's going to require a different identity to list. But cosecant alpha, cosecant beta times sine alpha, sine beta, well, sine and cosecant, they're reciprocals of one another, so we have that minus 1 there. And the last thing we need to do is we need to figure out what cosine alpha, cosine beta times cosecant alpha, cosecant beta is. So I'm going to do this kind of separate of this, and this is a step you wouldn't necessarily have to show on the proofs test. But cosine alpha, I'm just going to start with that, times the cosecant of alpha. Well, remember, cosecant is 1 over sine. So this becomes cosine alpha over sine alpha, which is cotangent alpha. So cosine times cosecant is cotangent. And so we're left with the cotangent of alpha, cotangent beta, minus 1 in our denominator, and that came from the quotient property. We had cosine over sine. And that's it. That's what we're trying to prove. So we're done with that one. All right, the last proof on this lecture looks like this, C, and it's actually relatively straightforward. There's just a lot of multiplying going on. So I'm going to start on the left-hand side, and I'm going to expand sine alpha minus beta and sine alpha plus beta, and then we'll do the multiplication that's implied there. So remember, sine alpha minus beta or alpha plus beta, it's sine, cosine, cosine, sine. So sine alpha, cosine beta, keep the sign the same, cosine alpha, sine beta. That's our first expansion. Now we're going to expand the sign of alpha plus beta. That's sine alpha, cosine beta. Keep the sign the same, cosine alpha, sine beta. And then I'm going to list that as the composite, right? That was the sum difference identity. I'm going to do the multiplication. I'm going to actually FOIL these two binomials to multiply them together. So what we get is we get sine squared alpha cosine squared beta minus cosine squared alpha sine squared beta. And the middle terms, they cancel because we have a minus cosine alpha sine beta and then a plus cosine alpha sine beta. This is a minus b times a plus b, essentially. Okay, no identity to list there, so we move forward. And we're trying to get to sine squared alpha minus sine squared beta, which means we want to get rid of these cosines. So I'm going to use the Pythagorean identity here to get rid of the cosine squareds. I'm going to say cosine squared beta is 1 minus sine squared beta from the Pythagorean, and then cosine squared alpha is 1 minus sine squared alpha. And then we still have sine squared beta on the outside, and that came from the Pythagorean identity. All right, so I'm going to clean this up. I'm going to distribute the sine squared here. I get sine squared alpha minus sine squared alpha sine squared beta. And then we want to be really careful about this last term here because we have a negative that has to get distributed in and also the sine squared beta. So what happens is we get minus sine squared beta and then plus sine squared alpha times sine squared beta. So just be careful on your signs there. There was no trig identity used. We're just doing some math. So what happens then is these sine squared alpha, sine squared betas, they cancel. We have a positive and a negative, and then we're left with sine squared alpha minus sine squared beta, which is exactly what we were trying to prove on the right-hand side. So we're done there. All right, so then the last three examples we're going to work through here, they relate more to using those composite identities in order to help us evaluate something. So we're not proving anything. There's no equal sign here to show what this is actually going to equal. We have to actually just figure it out. So the main takeaway here is to be able to look at an example like example D and see that the core of this problem is the sine of some angle A plus some angle B, where inverse sine of 1/2 represents angle A and inverse cosine of 0 represents some angle B. Anytime we're using inverse trig functions, we're getting angles as our final answer. So I don't know what they are yet, but we do know A is represented by that first angle, inverse sine 1/2, and B can be represented by the angle whose cosine is 0, which is that second component there. So let's actually just figure out what those two angles are, and then we can see what happens from there. Now, 1/2 and 0, those are unit circle values, so we can actually just use the unit circle to evaluate this. Angle A comes from the inverse sine of 1/2. That is asking what angle has a sine value of 1/2. And remember, inverse sine outputs angles in the first or the fourth quadrant. So we're going to look in the first or the fourth quadrant for an angle whose sine value is 1/2. That is the angle pi over 6. And then we move on to that inverse cosine of 0. Now that is asking us what angle has a cosine value of 0 within the range of inverse cosines. Remember, inverse cosine here is going to output an angle in the first or the second quadrant. There's only one angle with a cosine value of 0, that is pi over 2. So from here, we can actually use the expansion of the sine of A plus B, or we could just add these two angles together and see what happens. So pi over 6 plus pi over 2. Now pi over 2 is the same thing as saying 3 pi over 6. So that's 4 pi over 6 on the inside, which is the same thing as saying the sine of 2 pi over 3. We can actually calculate that. That's a unit circle angle. The sine of 2 pi over 3 is root 3 over 2. That's our final answer there. So some of them are as straightforward as that, using the unit circle to actually evaluate. But the next couple of examples are going to be a little trickier. So the last two examples we're going to look at today, E and F, they are doing the same thing as example D, but we're not going to see all of the angles being unit circle angles anymore, which means we're going to have to maybe draw some diagrams and see where to go from there. Now, example E, we still have two angles here. I still have the inverse sine of 5 over 13. That is the angle whose sine is 5 over 13. And then inverse tangent of negative 3/4, that is the angle whose tangent is negative 3/4. So the core of this problem is the cosine of A minus B. We have an expansion for the cosine of A minus B. We just need to figure out what those two angles actually are. Now 5 over 13 and 3 over 4, those are not angles on the unit circle, or they're not values on the unit circle. So let's sketch these angles and actually see what that's going to look like. Okay, inverse sine of 5 over 13. Inverse sine is going to output an angle in the first or the fourth quadrant. Because 5 over 13 is positive, this is going to be an angle in the first quadrant. And in order for that angle to have a sine value of 5 over 13, the y component here must be 5 and the hypotenuse is going to be 13, which makes the x component 12 because 5, 12, 13 is a Pythagorean triple. I'll label that angle A. Okay, I'm going to color code, so I'm going to do angle B here, represented by the inverse tangent in blue. So again, inverse tangent, same thing as inverse sine, the range, first or fourth quadrant. Now this time, it's negative 3/4. The tangent here is negative, which means we're going to be in the fourth quadrant. I'm going to drop my angle in the fourth quadrant, and then for this angle to have a tangent value of negative 3/4, the y component must be negative 3 and the x component must be 4, which makes the hypotenuse 5, again using the Pythagorean triples here. So that's angle B. Now, eventually, we're trying to get to what is the cosine of A minus B. Now, we have an expansion for the cosine of A minus B. It's cosine, cosine, sine, sine. Cosine, cosine, sine, sine. We change the sign for the expansion of the cosine of A minus B, or A plus B. And then I'm just going to use the diagrams to fill in what we know about these things. So the cosine of A, we look at angle A here in purple. The cosine is 12 over 13. And then the cosine of angle B, go to the blue angle, that cosine is 4 over 5, it's x over r. And then we go back to the purple angle, angle A, to get the sine value here, which is 5 over 13, and then the sine of angle B in the blue diagram is negative 3/5. And then we just simplify. This becomes 48 over 65 minus 15 over 65, which is 33 over 65. Just box that as our final answer. Don't think we can simplify that. All right, last example that looks like this, and then your homework problems will look very similar. We have the tangent of some angle A plus some angle B, and this one's a little bit nicer because angle B, we already have it, it's pi over 6. But we don't know anything yet about the angle A, except for that sine is 3/5. So we're gonna have to draw a diagram for angle A here because it's not in the unit circle. But the core of our problem is the tangent of some angle A plus some angle B. We have an expansion for the tangent of A plus B. We'll get there. First thing I'm gonna do though is I'm gonna draw my diagram for angle A. This is an angle whose sine is 3/5. It's positive 3/5, so we're in the first quadrant. For that angle to have a sine of 3/5, the y component must be 3. The hypotenuse must be 5, which means the x component here must be 4 using the Pythagorean identities, or Pythagorean triples. Okay, so that's our angle A. We already know what B is, so I don't need to draw a diagram for B. We can go straight into the expansion for the tangent of A plus B. Tangent of A plus B. Tan, tan, 1 tan, tan. Tan, tan, 1 tan, tan. So tan A plus tan B, and then this is all over 1, change the sign, minus tan A times tan B. And then we fill in what we know from the diagram here. So the tangent of A is 3 over 4. And then the tangent of B, now B, we have to actually use the unit circle here. At pi over 6, what is the tangent? So pi over 6, remember, that has a y component that is 1/2 and an x component that is root 3 over 2. So the tangent there is 1/2 over root 3 over 2, which is 1 over root 3. And I'm not going to worry about simplifying that right now. I'm just going to plug that into my expansion here first. All right, and then this is 1 minus 3/4 times 1 over root 3. Great. Okay, so we're here. What I'm going to do is I'm going to find a common denominator in the top and the bottom, and then kind of simplify the numerator and the denominator, and then go from there. Now, on the top, 3 over 4 plus 1 over root 3. Well, the common denominator there is going to be 4 root 3. So this first term needs a root 3 over root 3. This is going to be 3 root 3 plus 4 over 4 root 3 on the top. And then our bottom also is going to have a common denominator 4 root 3. So that is going to be 4 root 3 minus 3 over 4 root 3. And then something nice really happens here. Those 4 root 3's cancel, and we are left with 3 root 3 plus 4 over 4 root 3 minus 3. And then it's some algebra here. We have to rationalize. Got to get rid of the radical in the denominator. So we're going to take that denominator, we're going to multiply by the conjugate of the denominator. And then it's just a lot of foiling and algebra from here. So in the top, we are going to have 12 times 3 plus 16 root 3 plus 9 root 3 plus 12 all over 16 times 3 minus 9. And then I'm just going to clean this up by simplifying here. So 12 times 3, that's 36. So 36 plus 12 is 48. And then we have two like terms in the top here at those root 3, so 16 plus 9, that's 25 root 3's. And then this is all over 16 times 3, that's 48, minus 9 is 39. So this is all over 39. So that's our final answer. Box that, do your homework the same way. Email me if you have questions.